We're a scientific husband and wife team that spent 5 years working with Dr. Alhidi and other specialists, acknowledged in the last slide of this presentation, to study and manage Dan's normal tension glaucoma, primarily using high-res OCT. A surprising finding was that glaucoma progression, as measured by RNFL loss, had a strong quantifiable relationship to strenuous activity, but little to IOP. Note that we are unaware of any other attempts to quantitatively predict RNFL loss based primarily on physical activity. Helpful links are provided on the abbreviation slide for those new to eye and glaucoma science. This and related presentations are available at our central links site in the form of videos, Google Slides, or printable PDFs. When viewing on Google Slides, the home link icon on later slides will take you back to this content slide. We begin with reviewing the 2017-19 large retinoschisis events that first got our attention, followed by the 2021-23 OCT follow-up study that established the link between strenuous activity and RNFL loss. Some common abbreviations from the eye world used in this presentation. We've also introduced 5 new terms in bold related to the effect of strenuous activity on glaucoma progression. Note we distinguish the commonly measured resting IOP, the target of most glaucoma treatment, from active IOP, which refers to the difficult to measure IOPs experienced during active periods. Also note laminar fluid influx refers to fluid from the lamina cribrosa that flows into the prelaminar region, unrelated to the term laminar flow from physics world. The subject is typical of some normal tension glaucoma patients with myopia, extensive peripapillary atrophy, normal IOP, lowish cerebrospinal fluid pressure, and family history. IOP was measured twice daily with a home tonometer and kept near 15 by adjusting glaucoma drop use. The subject has been on modest testosterone replacement therapy since 2009 to maintain normal male testosterone and estradiol levels. The subject's history of NTG diagnosis, posterior vitreous detachments, and some retinoschisis are also not unusual. However, things changed dramatically after the fall of 2017, beginning 5 years of bilateral accelerated RNFL loss. Question: so what happened to trigger such significant RNFL loss? Several days of very strenuous activity while installing a sprinkler system triggered major right eye retinoschisis that eventually threatened central vision, followed by significant RNFL loss. The RNFL loss rate of 4 micrometers per year during the lengthy retinoschisis was quite high compared to typical less than 1 micrometers per year global loss for healthy subjects. Weekly OCTs were obtained and analyzed throughout most of this period in an attempt to understand and ultimately control what was happening. So what did we learn during this initial study? Both eyes eventually experienced major retinoschisis, with fluid 1 originating from the inferotemporal lamina cribrosa moving into inner and outer retina in direction of the macula. Inner retina fluid 2 was associated with RNFL loss, but outer retina fluid 3 was not. However, some RNFL loss also occurred in areas without obvious fluid influx 4. Raising IOP, lowering IOP, and Avastin had little effect on fluid influx rate, suggesting a non-neovascular source of fluid not readily influenced by changes to IOP in the range of 12 to 18. On the other hand, during the period of maximum right eye fluid influx, after an overnight drop in IOP from 18 to 12, fluorescein angiography revealed fluorescence at influx site 1, indicating a vascular origin 5, suggesting the simple hypothesis that physical activity leads to vessel leaks and subsequent RNFL loss, but with varying fluid influx and accumulation. Interestingly, fluid influx in both eyes slowed after modestly raising testosterone and estradiol levels, 7, estradiol coming from aromatase conversion of testosterone, echoing estradiol's use in suppressing nosebleeds, which would also support a vascular origin. See our references slide for a brief review and more info about glaucoma's association with physical activity, disc hemorrhages, lamina cribrosa defects, and sex hormones. The left eye confirmed all right eye observations. In this case, major left eye retinoschisis resulted from strenuous lawn dethatching, followed by head-down back stretching to address backache, creating venous pressure and active IOP spikes, 6, plus NSAID use, increasing bleeding risk, 7, ended by influx reduction after increased testosterone and estradiol, all suggesting again a vascular hypothesis for influx. In addition, deep LC fluid changes were found to precede retinoschisis fluid changes, directly confirming laminar fluid influx as the source of most retinoschisis fluid. Questions: can this system be managed to minimize RNFL loss? What exactly needs to be monitored and controlled? IOP, retinal fluid, exertion, posture, fitness, hormones? We propose studying this system more closely with frequent high-res OCT scans to help clarify cause and effect, but first needed to address a few technical issues. The Heidelberg Spectralis was the only OCT machine available to us that could be used to precisely measure RNFL and retinal thickness and fluid pocket areas at specific locations. However, its built-in algorithmic support for such measurements was too imprecise for our purposes. This led us to rely on use of its manual measurement tools, combined with special attention to proper scan positioning, to make very precise measurements of RNFL and retinal thicknesses and fluid pocket areas, examples of which are shown. Most importantly, small changes to site-specific RNFL thickness could be reliably measured over time compared to the noisier built-in support. Next, since fluid accumulation and RNFL loss tended to be localized between major retinal blood vessels, and major blood vessels interfered with making direct, precise RNFL measurements, we adopted a simplified sector numbering scheme based on vessel pairs for the superior, temporal, inferior sectors, where most RNFL is lost and is best visualized with OCT. This numbering scheme was used to specify locations throughout the optic nerve head and bordering RNFL and choroid. RNFL losses were measured and reported on a sector basis, such as -3 micrometers at L3, where average sector angle is about 24 degrees. In general, precise sector-based values, or totals and averages of such values, were most informative, corresponding to damage tied to specific optic nerve head locations. For comparison, sector values can be converted to global values by multiplying by the ratio of sector degrees to global degrees of interest. For example, a 3 micrometer loss at L3 would be 3 times 24 degrees over 360 degrees, equal to about 0.2 micrometers global loss for the left eye, or half that for bilateral global loss across both eyes. For the follow-up study, we chose a set of scan types: weekly high-res optic nerve head and triplicate RNFL circle OCT scans that supported close monitoring of changes to fluid accumulation and RNFL thickness. Note that most retina and choroid measurements were made using the Spectralis 1:1 micrometer display mode at 400% zoom, where 1 pixel is about 1 micrometer. For RNFL, precise measurements were obtained using the 1:1 pixel mode at 400%, which greatly exaggerates the apparent angle of measurement across the RNFL, but which is accurate if the measurement is kept vertical, matching measurements taken in the 1:1 micrometer mode, as well as the Spectralis built-in but less precise RNFL thickness measurements. Our expectation was that fluid changes being related to vessel leakage would be predictive of RNFL loss, with fluid at specific sites acting as canaries or sentinels. The canaries would then be associated with specific activities, revealing more about the causal chain activity to fluid to RNFL loss. But things turned out to be much simpler than that. So what did we find? During the 2021 to 23 study period, RNFL loss was about half that compared to the period 2018 to 19 with major retinoschisis, but still high compared to healthy subjects. The plot shows mean bilateral RNFL thickness, the average of all 20 sectors. In practice, we monitor each of the 20 sectors in separate plots. Loss was sector-specific, sometimes associated with laminar fluid influx, with some sectors being quite vulnerable while others quite resistant. Losses were discontinuous, occurring in roughly 8-week blocks, and initiated by one or more non-resting IOP factors. Interestingly, reducing IOP with Repressa before a significant RNFL loss had occurred was not helpful in preventing or slowing subsequent RNFL loss. So what were the non-resting IOP factors initiating RNFL loss? The main non-IOP factor initiating RNFL loss appears to be multi-day clusters of strenuous activity, date and duration of which are shown by the vertical red dotted lines in the plot. Each cluster's total micrometer loss was the sum of the micrometer losses at each affected sector during the 8 weeks following the cluster, where we can divide that by 20, the total number of sectors, to get mean bilateral loss. Note that clusters B, C, D, E were considered together since their 8-week RNFL loss periods overlapped. Interestingly, the number of sectors affected by a cluster rose smoothly with the number of micrometers lost. To review, clusters of relatively ordinary activity drove subsequent RNFL loss that took about 8 weeks to complete. A major insight on its own, but begging the question, what characteristics of these strenuous activity clusters determine their impact on RNFL loss? And is this relationship quantifiable? In other words, for this subject, can RNFL loss be predicted from strenuous activity? Strenuous activity time and intensity were the obvious factors to consider, but there's no info available as to how to weight these relative to RNFL loss. The simplest approach giving the most consistent results for RNFL loss was that shown, where strenuous activity time, SAT, was defined as the product of activity time and intensity, with intensity corresponding roughly to the low, moderate, vigorous levels described by others. Note no free pass was given for moderate exercise. In addition, extra intensity was assigned to activities involving some head-down posture and to those performed at high temperature or humidity. The SAT for a cluster then was the sum of the individual SATs accumulated during the duration of the cluster, ended by many days of more sedentary behavior. So how did RNFL loss vary with cluster SAT? Well, all those tedious measurements really paid off. RNFL loss appears to be a simple function of strenuous activity time. Regarding measurement uncertainty, note that although our numerous precise RNFL measurements made it easy to detect each sector's RNFL loss within plus or minus half a micrometer, and historical strenuous activity times within plus or minus a quarter hour, summing these for a cluster increased total uncertainty, which was accounted for by calculating the root sum of squared uncertainties, shown here by each cluster's error bars, and approximated by the plotted marker size. To summarize how we got here, precise RNFL measurements across 20 sectors, both eyes, over long time periods, for many different clusters with varying activity types, revealed a simple relationship. In other words, we had to take a lot of measurements under varying conditions to average out the noise in the system to see this underlying simplicity. So what mathematical function best fits this relationship? The relationship of RNFL loss to strenuous activity time, SAT, had 3 key features. 1, a rapid rise in RNFL loss with SAT. 2, a maximum SAT sub m below which RNFL loss is considered tolerable. And 3, a possible small background RNFL loss rate, K0, when fully sedentary. The simplest good fit was a third-order power function with strenuous activity coefficient KSR equal to the slope of a micrometer loss versus SAT cube plot, and a possible small background loss rate, K0, equal to the intercept of the plot. Note that various types of estimation are greatly facilitated by such a simple relationship. For example, even without knowing anything about KSR, compared to a SAT of 1 hour, 2 hours was about 2 to the third or 8 times, 3 hours was about 27 times, and 4 hours was about 64 times riskier than 1 hour. In general, breaking strenuous activity into smaller isolated times greatly reduced RNFL loss, whereas combining activities into larger clusters greatly increased RNFL loss. A few additional observations about the relationship. Lower order functions gave a poorer fit to the data, and only third order could make sense of BCDE's combined loss of just 20 micrometers after 20 total SAT hours, compared, for example, to A's loss of 29 micrometers after just 9.4 hours, independently confirming the third order fit and that it really pays to break a big SAT into smaller chunks. Also note that the third order function best predicted total bilateral loss across all 20 sectors. As uncertainty grew, the correlation coefficient fell, with less data in fewer sectors, illustrating how noisy and less predictable the system becomes when considering a single sector reacting to a single leak site in response to specific activities. Finally, RNFL loss appears to be unrelated to cluster resting IOP. In fact, the lowest cluster IOP was associated with the greatest loss, In addition, for this subject, we can say that strenuous activity is a modifiable risk factor for RNFL loss, whereas bouts of high active IOP are difficult to measure, have a poorly defined relation to activity and RNFL loss, and may be confounded by accompanying venous pressure spikes having a more direct effect on vessel leakage. Thus, activity truly trumped both resting and active IOP. Now let's try modeling RNFL loss during 2021 to 23 using our simple function, something we're pretty sure you've never seen done before. A model based on estimates of cluster strenuous activity times and KSR, combined with an 8-week RNFL loss period, produced an excellent fit to mean bilateral RNFL loss measurements during 2021 to 23. A slightly better least squares based model fit to the RNFL data was obtained using a value of about 0.6 micrometers for K0, the background loss rate when sedentary. However, this small K0 is equivalent to less than 0.2 micrometers per year global RNFL loss, which is easily accounted for by less than 2 hours of strenuous activity time per week. In other words, the apparent background rate was most likely just an artifact of our not counting the small effect of strenuous activity times between clusters, implying K0 is about 0, with strenuous activity time accounting for all RNFL loss in this subject. A surprising result, and meaning that while there's no free pass for small strenuous activity times, there's probably also no other process needing treatment beyond that tied to strenuous activity effects. So what's the link between this simple model of the 2021 to 23 data and the 2018-19 retinoschisis events? Is there a single simple mechanism that can tie all this together? This slide reviews the evidence previously presented for vessel leakage being the underlying mechanism for fluid influx, retinoschisis, and RNFL loss in this subject. Strenuous activity appears to increase risk of such leakage, although its effect varied from being minor to major, depending on activity length, intensity, and clustering, and where runaway refers to a vessel leak made so large that it creates a large pocket of adjacent fluid, retinoschisis, being absorbed by surrounding tissue, which reduces fluid pressure outside the leak, likely increasing vessel leakage and susceptibility to strenuous activity, making RNFL loss less predictable. With respect to clustering, note that activities with a modest strenuous activity time might be relatively harmless in isolation, with leakage receding over a few days, but produce significant RNFL loss if repeated several times in 1 week, with each modest activity increasing total leak volume and subsequent RNFL loss. Finally, the very rapid increase of RNFL loss with SAT cubed may simply be due to larger vessel breaks, both leaking at a faster rate and staying open longer, producing much larger leak volumes. So if it's mainly about vessel leakage, often tied directly to fluid influx, would it be better to track measured fluid, our original thinking, rather than estimating strenuous activity time? Measured fluid turned out to be far inferior to estimated strenuous activity time as a predictor. For example, OCT images from cluster F near sector R2 illustrate a critical point about 1 week after strenuous activity began, where leakage and damage to RNFL was still ongoing, but was soon stopped after reducing strenuous activity, avoiding creation of much larger retinoschisis, like that seen from near this site in 2018 to 19. Although this fluid influx and accumulation is likely connected to the process driving RNFL loss, the timing, volume, location, toxicity, and source of such fluid vary so greatly between events that tracking it turns out to be a poor way to anticipate future RNFL loss. Not to mention how impractical it would currently be for others to track such site-specific fluid influx with high-res OCT in short time frames, and especially when compared to simple estimates of strenuous activity time already shown to have a strong relationship to RNFL loss. On the other hand, tracking fluid influx and accumulation when present was the only way with OCT to monitor real-time leak site activity, while also confirming when absent that strenuous activity time was being properly managed. Thus, in practice, we found it useful to continue to track fluid influx and accumulation to get the most complete picture, particularly for real-time monitoring of individual active leak sites, where the SAT theory does a poor job of predicting individual site behavior, while RNFL loss takes another 8 weeks to complete, typically long after the site has become inactive. This slide reviews the key findings from our 2021-23 study. For this subject, glaucoma progression, as measured by RNFL loss, was driven mainly by clusters of strenuous activity, the total time and intensity of which had a strong, well-defined relationship to RNFL loss, where it took about 8 weeks after each cluster for RNFL loss to complete, and where the strenuous activity coefficient, KSR, likely varies with glaucoma type, stage, history, and subject. There was no evidence for any RNFL reducing process other than that related to strenuous activity, progression being minimized by simply keeping weekly strenuous activity time below the level at which calculated loss was considered tolerable. Note, however, that other factors related to this process, such as those affecting vessel leakage, may affect the likelihood of triggering RNFL loss by strenuous activity. Finally, IOP in the range of 12 to 18 appeared unrelated to RNFL loss. However, IOPs greater than 18 were part of the earlier history of this subject, possibly helping to create the conditions driving the current relationship of activity to RNFL loss. Also, IOPs less than 12 might be protective by improving ocular blood flow and reducing LC stress, but offset by any increased vessel leakage at lower IOP, making it unclear what net effect keeping IOP below 12 might have for this subject. So why has this simple relationship between activity and RNFL loss remained hidden? First, varying KSRs, the need to consider clusters, the cubic function itself, and the 8-week delay in RNFL loss all add to confusion, obscuring the relationship between RNFL loss and strenuous activity. Second, it's technically difficult to accurately measure small RNFL thickness changes relative to associated strenuous activities. And third, there's an understandable reluctance by many to consider moderate strenuous activity as potentially harmful. Given all these considerations, it may well be that strenuous activity plays a larger role in other glaucoma cases than current wisdom or practice would suggest. For this subject in particular, physical activity clearly trumped IOP, and progression was minimized with easily adopted behavior changes.